Topic 4.2, traveling waves. We have the only equation, wave speed c equals frequency f times wavelength, lambda. Let's make some traveling waves. So imagine we have a rope, it's secured to a table, and we're going to send a single oscillation down the rope. So to do that, we'll move our hand up and down while holding the rope, and there we go, there's our vibration. It's attenuated once it reaches the end here of this fixed boundary. We can repeat this motion to produce continuous traveling waves. So up and down, up and down, up and down. As we're moving up and down, you can see that those waves travel from left to right, but note that the rope itself doesn't travel to the right. It's only the particles making up the rope. They are temporarily displaced up and down while this pulse travels to the right. Let's replace that rope with a spring, and the spring will be once again secured at one end. And we can send a pulse, one pulse down by compressing the spring, and you can see this pulse travels and is attenuated there in the animation. We can also repeat this motion continuously. You can see that these pulses move back and forth. Note that the spring as a whole does not travel to the right. Again, the particles in the spring just vibrate left and right locally. The rope and the spring are both examples of traveling waves. Both of these traveling waves moved in the positive x direction, to the right. The material through which a wave propagates is called a medium. So we've seen two examples of mediums, a rope and a steel spring. Now the rope transferred its wave pulses by these vibrations which were perpendicular to the direction of the wave velocity. So let's pulse this wave again, and you can see that as the wave travels to the right, the particle, the wave itself, or the rope, the particles making up the rope travel up and down, are displaced up and down. So any wave produced by vibrations that are perpendicular to the direction of motion is called a transverse wave. The spring transferred its wave pulses by vibrations which were parallel to the direction of the motion. So again, we have the spring, we pulse it, and you can see that that pulse traveled laterally, parallel to the direction of motion. This type of wave is known as a longitudinal wave. And note, for all waves, energy is being transmitted, not matter. The particles making up the spring, the particles making up the rope, are not permanently displaced. They vibrate, but they come back to their original position. Only energy is transferred. Sound waves are longitudinal waves that form due to the propagation of sound energy through a medium. In air, sound waves create areas of high pressure called compression and low pressure called rarefaction. So you can see that the areas of high pressure compression are along these fronts here, traveling very fast. Low pressure, we have this spread out, these spread out regions. Air molecules oscillate back and forth between these areas of high and low pressure, but their displacement is zero. So we can graph a longitudinal wave as a pressure versus time graph. Here I would have pressure on the y-axis, or the vertical axis. The horizontal axis would be time, and I'll draw a complete cycle for an oscillation. And this, the x-axis, or a place where y equals 0, we would have atmospheric pressure right here, and here we would have compression, so the pressure would be greater than the atmospheric pressure, and then here we would have rarefaction, places where the pressure is less than the atmosphere. I can also graph displacement versus distance for particles in a sound wave or any type of longitudinal wave, which is very interesting. I'll sketch maybe 1.5 wavelengths. Okay, so where you have, this is displacement on the vertical axis, and this is distance on the horizontal axis. So what happens in a displacement versus distance graph is particles that are positively displaced are moving to the right. So these particles are moving right, moving in positive direction, or whatever the orientation is. Again, they're moving in a positive direction. Particles that are moving in a negative direction are sketched below the x-axis. Negative direction. You should copy this down. So imagine I'm looking at a particle right here. Could you tell if this particle is experiencing a region of low pressure rarefaction or high pressure compression? Well, you would look first in this direction here. So particles to its left that are to the left of this particle, because this is distance here on the x-axis, are moving in the positive direction, are moving to the right. So these particles are coming in. The particles that are to the right of it, I'm looking over here, they are moving in a negative direction. So this would experience a squeeze of particles. This would be a high pressure. If I look at a particle, let's say right here, I do the opposite. I'm looking and I see that these particles are moving in a negative direction. They're still moving in a negative direction, so particles are moving away. Particles to the left of this purple dot are moving away, and let's see up top. These particles are moving in the positive direction, so they're going to the right, which means that all of the particles on either side of this purple dot are moving away from it. This would be an area of low pressure here, rarefaction. Rays are arrows that show the direction of wave propagation. They show the wave velocity. They're always drawn perpendicular to the wave fronts. So I have concentric circles. These could represent transverse waves like water waves. They could represent longitudinal waves, sound waves, but for any type of wave, longitudinal or transverse, the rays are always drawn perpendicular to the wave fronts. A wave of period 5 milliseconds travels through a medium. The graph shows the variation with distance c of the displacement x of points in the medium. What is the average speed of the points in the wave? So be careful. One wavelength is, this is a cosine graph, goes from 0 to 2. One wave itself would travel 2 meters in 5 milliseconds. However, the particles don't travel 2 meters. It's the energy that travels 2 meters in 5 milliseconds. Rather, the particles will oscillate up and down in one period, in one oscillation. So they'll go from 2 to -2, and then from -2 back up to +2. That's what the points are doing in the wave. So speed equals distance over time. And in this case, we have to be careful about what distance we're talking about. It's not the distance traveled by this oscillation, it's the distance traveled by the points that are vibrating. So from 2 to -2, that's 4 centimeters, and then returning up to starting position would be 4 centimeters. That's a total of 8 centimeters distance traveled. Divide that by the period of this oscillation, and that'll give you the average speed of the points in the wave. Practice 2. What is the correct description for the direction of a ray drawn relative to a wave front for longitudinal and transverse waves? Hopefully you remember from the previous slides. Practice 3. What is the correct description for the direction of energy propagation and particle oscillation for longitudinal and transverse waves? If you remember the definition for a transverse and a longitudinal wave, this one should be really easy. What is the minimum distance between the crest and trough for any wave type in the direction of energy propagation? So let's sketch a wave. This is one complete wave. Not quite. There we go. Okay, so from here to here, from end to end, this represents a full lambda. This is a cosine graph. So then what is the distance between a crest, which would be here is a crest, here is a trough? That would be lambda over 2. The speed at which a crest is moving is called the wave speed. This is really a measure of the rate at which a disturbance can travel through a medium. Since the time it takes a crest to move one complete wavelength, lambda is 1 period, capital T, the relation between V, lambda, and T is V equals lambda over T. Frequency measures how many wave crests per second pass a given point and is measured in cycles per second or hertz. Again, frequency is the inverse of period, so we get this relationship F equals 1 over T. Graph 1 shows the variation with time t of the displacement y of a traveling wave. Graph 2 shows the variation with distance x along the same wave of its displacement. Determine the amplitude and wavelength of the wave motion. So one graph is displacement versus time. One graph is displacement versus distance. So only graph 2 will give us information about the wavelength. So I can see if I sketch out one complete wave, the length of this wave is 0.3 centimeters. Now I can use either graph to determine the amplitude. Amplitude is the maximum displacement from equilibrium. So the amplitude can be measured here or here. I'll just use the magnitude of the amplitude. It is 2.0 millimeters. Part B, use the graphs to determine the period and the frequency. So I can use graph 1 to determine the period and frequency because it contains time information on the x-axis. Again, one wave is this. So that is from here to here. So the period, capital T, equals 0.25 milliseconds. Frequency equals 1 over 0.25 milliseconds. Part C, determine the wave speed. I will need both graphs for this. Wave speed is distance over time, so I get my distance information from here. C, I'm going to use C for wave speed. C is 0.3 centimeters divided by, and I can use the graph 1 again for my time information, divided by 0.25 milliseconds. This gives me a wave speed of... The diagram shows, at a particular instant in time, part of a rope along which a wave is traveling. The direction is traveling from left to right. Which arrow gives the direction of motion for a particle at the point on the rope? So we're looking right here. This is the point. And to figure out where the point is going to be traveling, you look at what wave fronts are coming towards it. This wave front has already passed. This is what's coming for it. This is up next. Okay, so based on that, I can see that what's coming next is a crest. That means that this wave is going to be traveling in the x direction. And you can see just like this, what's coming next is the direction that this little yellow particle will travel in. A transverse wave travels from left to right, just as before. The diagram below shows how, at a particular instant of time, the displacement of particles in the medium varies with position. Which arrow represents the direction of the velocity of the particle marked P? Again, look what's coming up next. This is already past. This is what's coming next. Which way is the particle going to move? We're all familiar with visible light, but this light is just a tiny fraction of the complete EM spectrum. The EM spectrum ranges from long wavelength, low frequency radio waves to short wavelength, high frequency, high energy gamma rays. Visible light comprises just a small portion of this, and it ranges from red to violet, red having 700 nanometers of wavelength, and violet is 400 nanometers, higher energy. This is lower energy, higher energy. In free space, that is a vacuum, all EM waves travel with the same speed, 300 million meters per second. C is the symbol for light speed, though I still use C for other wave speeds. C equals lambda times F. The constant for the speed of light is given in the front of your data booklet, practice 8. The wavelength of a particular hue of blue light is 475 nanometers. What is its frequency? The graph shows one complete oscillation of a particular frequency of light. What is its frequency and what part of the spectrum is it from? So I can see a graph, it's displacement versus time, one oscillation. So I don't need the displacement information. That would tell me information about the intensity of the light. Don't need that. Instead, I can see that this period, time for one oscillation, is 6e negative 16 seconds. Frequency is the inverse of that, so what is the frequency? And then what part of the spectrum is it from? You can use the frequency Maybe you can see from here, or you can Google it. So what is the wavelength? Lambda equals the speed of light, c over f. So here's an animation of a moving electric charge producing a changing EM field that propagates through space at c. We can see that the red arrows represent the electric fields and the blue arrows represent the magnetic fields. They oscillate perpendicular with each other. The crests and troughs of each wave move to the right at the speed of light, and each region in space executes simple harmonic motion in the form of oscillating E and B fields.